I have started recording about 14 minutes early, so if you were watching this video, you can skip ahead 14 minutes. Had issues recently with recordings. They seem to stop early, so I wanted to start the recording process now, so I have 15 minutes while I wait for lecture to start to ensure that it is still recording. Hello. It's Reed, right?
Yep.
All right. Give you a little bit of extra credit since you were the first one here. So 2.1 points instead of 2. Doesn't sound like much, but all these little extra credit points add up. About to tell you your current total, but never mind, we're recording. Good morning.
Good morning.
Let's see. The Mankins?
Yes, sir.
Yeah. All right.
Morning.
Morning. And we got Rains in the back left, correct? Or back left for me, back right for you. Okay. Thompson.
Uh-huh.
Okay. So, it'll be Covington Griggs.
Yes.
I used to live in a town in Georgia called Covington, so every time I see your name, it reminds me of one of my hometowns. Case book? The Morgan all the way in the back? So far, I think everyone's accounted for. Kate the online. One. Hughes.
Yes, sir.
Is it Yandui?
Huh?
Last name Yandui?
Liberty.
Liberty. Oh, hey. Hey. Gotcha. Thanks.
You do that to me?
Yeah, number one. Yeah. I got like 85%. 85%. 91. I didn't pick up shit. It's what that is. It's just a little one day of notes.
Well, it's 8:01. I guess we'll get started. A couple more people show up, but they're not. Do announcements and reminders as usual. So your pre-lab, or excuse me, your lab from Wednesday, I guess I should say past due. It was due on Wednesday, it's past due as of tonight. It's still the first lab, so I don't feel like I'm harping on you if you don't know how to do this. But that needs to be uploaded. You have to, you did it with Google Docs. You need to download it as a PDF and then upload it to my online. And if you don't know how to do that, that's fine. Meet me online and I can show you how to do it. If you don't know how to meet me online, send me an email and I'll show you and I'll give you the information on how to meet me online. Likewise, your pre-lab is also due tonight. So again, like you did last week, some of you haven't figured it out yet. And again, I'm not judging, I'll help you do it. But the pre-lab is due tonight, and to turn in the pre-lab, you need to share the Google Doc with me. And as you can, for those of you who have done it that way, you can see why, right? Because I leave comments, and that's my way of giving you your feedback for the pre-lab. So make sure you do that tonight. Notice too that pre-lab is in bold, and the other one's not, right? So if you find yourself in a crunch, and you're like, I've got these two things due at the same time, prioritize the pre-lab. Because you have to get that done to come to lab next week. And I'm gonna grade the pre-labs before I grade, well, in theory, I'm gonna grade the pre-lab before I grade the labs. So prioritize that. Any questions about lab stuff? All right, the quiz is due on Sunday. To remind you, it's untimed, it's unlimited. There's no reason, it's open book, so there's no reason you should really get anything less than 100. Just keep taking it until you get 100. Every time you take it, there should be a different set of questions because this is the pool of questions that I'm taking to use to write the exam. Most of them will be rewritten, but they will be the same questions, just rewritten. So yeah, make sure you get that quiz done. I'll remind you this. I'm gonna remind you this a lot. Let me help you. Not so much with the quiz, there's not much I can do about that. But with the labs, so for example, when you're working on a lab, if you need help, I will help you. I know I say you're supposed to do it. It's not homework though, even though it is. I'm asking you to do it on your own. I'm telling you, you don't have to do it on your own. You can meet me online. I will walk you through each step. Read the introduction, explain what you need to know. Let me help you with that. Or before you turn anything in, let me look it over, right? And I can just quickly, it'll take 5 minutes. Like, hey, you might want to fix this. You definitely want to fix that. I'll give you some information. Or I can't grade this at all because you didn't do this or that, right? So if you want to, take me up on that. Let me help you. Speaking of which, really quickly, and that remind me, that pre-lab that's due tonight, remember, you have 2 short videos to watch, questions to answer before you do the pre-lab. And if you don't do the videos before you do the pre-lab, then you get a 0. So make sure you do the videos before you do the pre-lab. And if you've already turned in the pre-lab and I haven't graded it yet, and you haven't done the videos, you can sneak it by me, right? Just when we're done here, go watch the videos, answer the questions. So any questions about all that stuff? Again, please let me help you. Let me help you before you turn stuff in, and then afterwards, meet me online, let me give you detailed feedback. So then you can learn from your mistakes and get a 5% boost to that assignment's grade. Still want to remind you the first assignment I gave you was to read the syllabus. I have reason to believe only 3 of you have read the syllabus. If you read the syllabus, you'll understand how I know that. Don't forget to write some independent work. As of today, independent work is now worth 18 points per page instead of 19 or 20. Remember, it's supposed to be 10. I jumped it up to 20 to bribe you guys. Then I knocked it down to 19. Now I'm knocking it down to 18. So you want to start turning it in. It's going to start getting lower. Please try to be on time for lecture. Life happens, so I'm not saying there's anything wrong with you if you're not on time, but it is disruptive. And I've seen a lot of it, more so this semester than other semesters. So try your best to be on time. Today, we're going to do the usual attendance words. And then at the end, I'm also going to ask you to send 1 question about all the material that I've covered today. So as you're listening to this lecture, think about what your question might be. Even if you think you understood everything I said, just come up with a question anyway, right? Just to confirm that you understood it. Or you can pretend like you're writing a quiz question based on all this information I presented today. So are there any questions about my announcements and reminders? Yes, nice and easy. All right, in that case, do you guys have any questions or announcements? Like anything going on with your sport that you want us to come to or your student activity? All right. So today's, and first, before I start with the tennis words, I'm going to not do this again, probably start next week. I don't need to remind you guys this much. You will get it. So for you guys who are here, you don't have to send attendance words, but you can because then you'll get extra credit. For those of you who are online or watching the video, you have to send these extra credit, or excuse me, these attendance words as proof that you were paying attention. And the first word for attendance is peanut butter, because today is National Peanut Butter Day. So for those of you online, not you guys who are here, the people who brave the weather, but if you're online, don't send me the word peanut butter. We'll do this later, because you do it before 9 a.m. But send me tell me what your favorite peanut butter is, or send me a picture of peanut butter. But don't just send the word peanut butter. All right. Any questions? All right. In that case, I have a question for you, since none of you guys are biology majors. How many of you took biology because you didn't want to take chemistry? Oh man, it's a few. I'm afraid to tell you that's bad news for you, because today we start chapter 2, which is chemistry, the chemistry of life. How many of you had chemistry before? Oh, good. All right. So if you've had chemistry, depending on how in-depth it is, or it was, this might be easy for you, because we really just scratched the surface of chemistry. We're not going to be balancing equations. We're not going to be dealing with moles, and there's almost no math involved in the chemistry that I'm going to teach you. And I will also mention this. Again, I'm teaching out of, for me, a new textbook. The old textbook had 2 different chapters, chemistry and then biological molecules. But this textbook combines them into one. Not that that matters for you, but something seems a little bit out of place, a little bit out of order when you compare my PowerPoint to your textbook. That's why. So here we go. From the old textbook, we'll start the old guessing game. Of course, we're running a little bit behind, so I won't do it too much. But can anybody tell what this picture is? It's a little bit hard, but can you, like, overall, not necessarily this thing that's sticking out like a sore thumb, but overall, can you tell what that's a picture of?
Coral.
Coral, good, yeah. Any of you, have any of you been to a coral reef, just out of curiosity? I'm impressed that you know that then. First of all, it's a crappy picture, and second of all, it doesn't look like a typical coral reef. Yes, it is a coral reef. Anybody know what's going on with that particular piece of coral? Not that you need to, or that I expect you to, I'm just curious if you do. Nope, okay, it's dead, basically. It's dead coral.
What is that?
Huh?
What is that?
It's well, I don't know which particular species of coral it is, but it's a piece of coral that it's died. And the thing that your old textbook, the point they were making was like their analogy, if you will. They're saying the car exhaust from a car in Boston eventually will lead to contributing to the death of coral in the Great Barrier Reef. That's the exact wording. Well, that's paraphrasing from the old textbook. Of course, it doesn't have to be that far away. You know, it could be like the car in Miami killing the coral reef in Key Largo, but same concept. All right, what's going on here? Obviously, that's some fries, but what do you think they're putting on the fries?
Salt.
No, it's cocaine. No, I'm just kidding. Yes, it is salt. And this is interesting because what you're going to learn in this chapter is a little bit more about chemistry, and people try to scare you with chemistry. There's a lot of chemophobia out there because they'll say, ooh, you know, they put this ingredient in that food you're eating, and it's scary. And you know, they'll tell you something scary about that ingredient, and it is probably, well, I shouldn't say probably, it very well could be a true statement, but you have to understand chemistry to understand it's not necessarily scary. So does anybody know the two elements that make up salt?
And then sodium.
Sodium is one of them, yep. That's okay. And then chlorine is the other one. But technically when they're together, it's called sodium chloride. Anyway, sodium is an explosive metal. So when you put it in water, it explodes. You talk about dangerous, that's dangerous. Chlorine is a deadly gas. We literally use, well, we didn't. It's been used as a weapon in war to kill people. So somebody trying to scare you, like, you know, they put this deadly gas that literally they kill people with it, and they're putting it in your food. True statement. But when you put these two deadly things together, it's just salt, right? So people try to scare you after you get this class. Hopefully you're a critical thinker and you're less likely to be tricked and scared. Yeah. And another thing, speaking of salt, you need salt. You need salt in your body. You have to have it. You need it to do the things that your body does, and we'll talk a little bit about that this semester, or excuse me, this chapter. But just like anything else, too much of it's bad for you, which is another thing people try to scare you with as far as chemicals are concerned. They're like, you know, this is a toxin like fluoride. Yes, fluoride is toxic when you get too much of it. So is salt when you get too much of it. So is water when you get too much of it. So it's all about the dose. The dose makes the poison. Even things like fluoride, which you need, and salt, which you need, and other things we're going to talk about later. You need them, but if you have too much of it, it'll kill you. So be smart when people try to scare you with stuff, especially these days. There's so much misinformation going around. Anyway, the other picture's a bunch of copper pipes. Nothing to talk about that. So let's move forward. So this particular chapter, I know that's hard for you to read. It's broken down into 3 parts. The building blocks of molecules. Then we're going to talk about water, and then we're going to talk about biological molecules. So here we go. Let's jump into it. Man, that is really hard to read. So the learning objectives, if you can read them for this part, by the end you should be able to describe matter and elements, and you should be able to describe the interrelationship between protons, neutrons, and electrons, and the way in which electrons can be donated or shared between atoms. So that brings up a good point. What is an atom? I'm sure you probably all know what an atom is, but the hard part is right now when I'm asking you to tell me what is an atom. Like there's so many words where I know it, but then when someone says, hey, what is it? I don't know how to say it, but I know what it is. What do you guys think? What is an atom? ATOM, not like Adam Sandler or anything like that. Any guesses? Okay, I'll just give it to you then. And you need to know this for the exam. Each element consists of one particular type of atom, specific type of atom. So in other words, every individual element, so if you look back there, you can see the periodic table, they all have their own type of atom. And what is an atom? It is the smallest component of an element that retains all the chemical properties of that element. You don't need to memorize that verbatim because if I ask you what an atom is, I'm not gonna use that verbatim. Just understand what that means, right? It's the smallest piece, you know. In other words, you can't break it down anymore. Once you break down an atom, you no longer have an element. You just have parts of an element. And that'll make more sense as we go through this chapter. But so far, are there any questions about what an atom is? All right. Let's talk about what makes up an atom. You definitely need to know this. The three parts that make up an atom: proton, electron, neutron. You need to know that for the exam. You also need to know that a proton is positive and an electron is negative and a neutron is neutral. In my opinion, that's one of the things that's easy to remember because proton starts with a P, so that helps me remember that it's positive. Neutron sounds a lot like neutral, and it's neutral. And getting electrocuted is a negative thing, right? It's not a positive thing when you get electrocuted, so that's how I always remember electron is negative. Also process of elimination, right? Proton's positive, neutron's neutral. Therefore, by process of elimination, an electron is negative. Now, I'm going to beat this dead horse a little bit later, but I want to go ahead and introduce you to this concept right now. Imagine, like, we could actually see protons and neutrons and hold them. We can't, they're too small. If I like holding an electron right now, and you're in a neutral state, and I throw that neutron or that electron to you and you catch it, do you think it would still be neutral, or do you think it would be negative, or do you think it would be positive if I gave you an electron? You'd actually be negative, and that's a common mistake. So I wanted to introduce it now and then really talk about it later. So when something gains an electron, it's negative, right? So it becomes more negative. Hope that makes sense. If it doesn't yet, that's okay, because we're going to talk about it later. But yes, that's one of the things that confuses people the most. And again, we'll cross that bridge a little bit later today and definitely in next week's lab. So yes, an electron is negative. So if something gains an electron, it becomes more negative. If something gives up an electron, it becomes more positive. Also, and this will be a little bit more important later in this chapter, but protons have a mass of 1 and neutrons have a mass of 1. As far as we're concerned, electrons don't have a mass. This is a 100 level course. But for independent work, you can look that up. What is the mass of an electron? And then you can send in a paper that's 2 sentences long. I was wondering what the mass of electrons are. I looked it up, and according to this source, this is the mass. And of course, your source will probably go on to explain what that means, and you could also explain what it means. As long as you're not copying your source or rewording your source, right? Just if you copy your source and use their exact words, don't forget to use quotation marks. Anyway, so any questions about this top part? The parts that make the information about protons, electrons, and neutrons. All right.
What did you say we could write the paper?
Technically anything, but the idea I was giving you here is that I'm saying, according to us in this class, an electron has no mass, and that's what you need to know for the exam. But in reality, it goes a little bit deeper than that. You can look that up if you want to for an independent work. The mass of an electron. And if you start to read it and it starts blowing your mind because it's a little bit too deep, then just don't worry about it. That's the beauty of independent work. I'm not telling you have to write a paper about that. It's just a suggestion that if you look at it and it's boring you or confusing you, then forget it, move on. All right. So the next part. If the number, like we're looking at a particular atom, if the number of protons equals the number of electrons, in other words, if we want to talk about it mathematically, if you have the same number of plus ones as you have minus ones, then you have a neutral charge, right? Your charge is 0. It means it's neutral. That's another important concept, especially for your pre-lab. If I remember correctly, that's a pre-lab question. Not specifically that, but there's a question that involves like, hey, if this thing gains an electron or loses an electron, what's its charge now? If it's not a pre-lab question, it is a lab question next week. So any questions about this slide? Okay, so let's talk about, we're still talking about the structure of an atom here. We know the 3 parts. Now, there's something called a nucleus of an atom, which is different than the nucleus of a cell. But the nucleus atom is the central core, it's the middle of the atom. And what you need to know for the exam is what is in the nucleus. There you go, protons and neutrons. Electrons are just I don't want to say they're orbiting around the outside, but for this level of, for 100 level class, we could consider them orbiting. It gets a little bit more complicated than that. So what you need to learn and understand, in your mind, you can picture them as orbiting. But anyway, the point is, at least for now, protons and neutrons are on the inside, electrons are on the outside. Here's a quick quiz for you, since I just told you and it's not on this slide. What charge do protons have? Perfect, positive. Now, have you ever tried to put a magnet together, like, or two magnets together where it's the same side, and what do they do, like if it's the same side that you're trying to put together, what do they do? They repel, right? So if you try to put a plus and plus together, it repels. If you try to put a negative and negative together, it repels. Technically, what I'm about to tell you is not really about, and it's not important with this class, but the concept I will bring up later, and at that point it'll be important. But anyway, think about this. Look at all these protons. Of course, you're seeing more neutrons, but there's a lot of protons over in there, squished together. But just like a magnet, those things don't want to be together. They're repelling each other. But there they are, tightly put together. And the interesting thing about this is, if you think about it, that's got to take a lot of energy, right? Those things want to be pushed apart. Like, so imagine, I'm sure, like I said, I'm sure you put two little magnets together, they repel each other. Imagine having like two huge magnets and trying to put them together. That'd probably be impossible. So think about the energy it must take to keep those things so tightly together. And again, not that this matters for biology, but basically that's where nuclear energy comes from. There's so much energy in there that once you disrupt that and start breaking things, it just releases so much energy. That nuclear energy is not important for biology, well, not this course anyway, but this concept will come back a lot, at least in the beginning of the semester. Basically, what you need to know is however much energy it takes to keep something together, when you break that thing, that's how much energy is released. In this case, we're talking about nuclear energy, which is useless for this course, but later we're going to talk about other stuff, and I'm going to bring this concept up again. The more energy it takes to build something and keep something together, that's how much energy will be released. And for us, that is an important concept. Because remember, one of the first properties of life that you learned about last week is this energy, right? Energy has to be converted from one form to another, right? Life has to have energy. So that will be an important concept as we move forward. Anyway, again, back to the exam. What you need to know for the exam is the nucleus is on the inside, and it consists of protons and neutrons, and electrons are on the outside. Any questions about this slide before I show you another picture that shows a nucleus? Okay, there we go. This is another nucleus, right? So you can see we have two neutrons, two protons. I know it's helium because it has two protons. I'll explain that later. And then you can see the electrons on the outside. This picture's from your old textbook. I like this because it's more realistic. I like how it says electron cloud. So again, in all reality, it's more like a cloud of electrons. But for us in this 100 level course, probably the way you were taught, or maybe the way you were taught previously, is it's orbiting. And again, they're not necessarily orbiting, but for us, picturing them as orbiting is the way to go, because that will help you learn what you need to learn. Whew. So any questions so far about all this stuff? All right. Next word for attendance is beer can. Beer can. Because not only is today National Peanut Butter Day, but it is also National Beer Can Day. And once again, for you guys in person, if you're here, you send me the word. But if you're watching this online or watching a video, don't send the word beer can. Send me an actual beer can. I wish. I don't do that. Actually, no, that's not true. I will give you extra credit for bringing me brushed and dry aluminum cans. So that's a whole different story. I'll talk about that later. But don't bring me any full beer cans because that's bribery. And I think it's a dry campus, so don't do that. But anyway, yeah, beer can is the next word for attendance. And again, if you're online, send me a picture of a beer can or tell me your favorite beer. If you're old enough to drink. If you're not, I don't want to be implicated in your illegal activities. Anyway, here we go. Atoms of a particular element have the same unique number of protons. You definitely need to know this. This is very important. That first bullet point is very important. And there's another way of saying this. You could say that elements are defined by their number of protons.
Or you could say, if you change the number of protons in an atom, you change the element, right? So it's all about the protons when we're talking about what element it is. You cannot change the number of protons without changing the element. If it has one proton, that's hydrogen. Not that you need to memorize that. If you add a proton to that, then you have two protons, and that makes it helium, as the example that's here. If you have something with 7 protons, not that you need to know that, but that would be nitrogen. You take one away, well, you know what, we'll get there later. Anyway, that's it. You definitely need to know that, right? An element is basically defined by its number of protons. You cannot change the number of protons without changing the element. You can change other stuff, and it'll still be the same element. But if you change the number of protons, you change the element. And we call this the atomic number. And I don't know if I'm going to ask you to define what an atomic number is, but I'm definitely going to use that term a lot in this chapter, and in some of the other chapters, definitely in the lab. So you need to know what it is because I'm going to be using it. We're using helium as an example. So let me quickly put an X through here, only letting you know that this is just an example. So when you're studying, don't feel like you need to memorize anything about helium. I'm just using this as an example to teach you. But yes, helium happens to have 2 protons. Therefore, its atomic number is 2. Therefore, no other element has 2 protons. Right? Only helium has 2 protons. So any questions so far before we talk about the mass number? Okay, so like I said earlier, protons have a mass of 1, neutrons have a mass of 1. As far as we're concerned, electrons don't have mass. So therefore, the mass number of any atom is when you add up the number of protons and the number of neutrons. And you definitely need to know that. Like I said, there will be some basic math in this portion of the semester, because I'll probably ask you something like, for example, helium. We can see the mass number is 4. We can see the atomic number is 2, right? So we know if the atomic number is 2, by definition, that means it has 2 protons. Its mass number is 4. So we know it has 2 protons plus X amount of neutrons, and that gives us 4. So how many neutrons must it have? 2 plus what equals 4? 2, good. And that's the most basic kind of math you're going to get on the exam, other than some charged things that we'll talk about later. So yeah, you will get a question like that, where I might tell you the mass number of something and then say, how many neutrons does it have? And it'll be some very basic math like that. Any questions about this slide before we go to the next one? Okay. Moving forward. So this is where it gets a little bit confusing. And before I jump into it, I want to let you know, I'll do my best. You know what, let me say it like this. If you're still confused after I try to explain it, don't let it stress you out, because there might be 1 or 2 questions about it on the exam. This thing I'm about to teach you, and where you're going to have to distinguish the new stuff I'm about to teach you versus what's on here. If it confuses you and you don't get it, it's not the end of the world. It's barely going to affect your grade, and it's only slightly important to learn the stuff that we're going to learn later, right? A lot of this stuff you need to know. You need to know this before I teach you the next thing. You need to know that before I teach you the next thing. So this next slide, it's slightly important, but not very important. So if you can't understand what I'm about to teach you, don't stress out. You should be okay moving forward. So we know the mass number is the number of protons plus the number of neutrons. Then, to piss people off, chemists said, well, let's confuse people and have something called an atomic mass. And your textbook didn't explain it, but your old one did, so I'm going to explain it. It's similar to a mass number, but it may differ. I don't know if anybody can read it, but can anybody see up at the top left that hydrogen, what the mass number is?
One point 008.
1.008. It's been a while since I've done it. Okay, 1.008. Now think about that for a second. 1.008. Protons have a mass of 1. Neutrons have a mass of 1. You can't have a decimal when you add up whole numbers, right? That, to me, makes no sense, and I wish your textbook would explain that, because if you're a thinker and you're looking at this, you're probably thinking, well, this makes no sense. Where are you getting a decimal when we're talking about whole numbers? So here's how this works. It's similar to the mass number, but it's not the same. It may be the same, but usually it's not, but it also more likely will differ. And what it represents is the average of all naturally occurring forms. So what I can tell by this number right here, 1.008, that tells me that almost all the hydrogens in the universe must have a mass number of 1, because this number is very, very close to 1. But there must be a couple out there that have a mass number of 2, or maybe even a mass number of 3. There's obviously some that have more than a mass number of 1, because the average is slightly above 1. Does that make sense? But that's what this is. That's why I have these pictures. And I'm going to put it next to this, because you don't need to memorize anything about hydrogen. This is just an example. But yeah, and that's why. So what we're looking at, there's 3 different types of helium in the universe that we know of. There's H1, which just has the 1 proton, mass number of 1. Then there's H2, which has 1 proton and 1 neutron. H3, 1 proton, 2 neutrons. And again, not that you need to know this, but I can tell by looking at this number, or that number, it's even more precise. That number is so close to 1 that I can tell without even doing any math that most of the hydrogens in the universe must be this one, not this one, or not this one. And there's one more way to look at it. What is the average number of fingers that that all humans have on Earth? 8. Actually, I don't know the answer. I'm assuming it's not 10 though. Think about it. Some people have extra fingers, some people are missing fingers. So it's probably really close to 10. It's probably like 9.9995 or maybe 10.0001. I don't know. Point is, not everybody has 10 fingers, right? Or what's this one? There's another good one. Have you ever heard what's the average, and I don't know the answer to this too, but maybe some of you do. What's the average number of kids that Americans have?
2 or 3.
I really don't know. But I have heard, last time I heard, it was like 2 point something, or something point something, right? And it's not like somebody's got like two kids that are alive and then one that got killed in an ATV accident and lost its torso and they're just keeping around half a kid, right? No one has half a kid. Well, I guess you could make an argument against that too. Anyway, the point is, this is how averages work, right? So when you're talking about whole numbers and then end up with decimals, that's how. It's because we're dealing with averages. So one more time before I move forward, and just using hydrogen as an example, it could be any element. There is no hydrogen, not one single hydrogen in the universe that has that mass number, right? No hydrogen has that mass number. But if we average all the hydrogens up around the universe, we would get this. All right, so any questions about atomic mass before we move forward? All right, this next slide is not very important. It's just an introduction because you're going to have to use the periodic table a little bit in the lab. So you're going to need to be introduced to it. There's not going to be many, if any, questions about it on the exam. Periodic table of elements that you can see back there and that you'll see on the next slide. It includes at least the atomic number and the atomic mass of each element. Very often it includes other stuff. And again, you don't need to study this. I'm just introducing you to it. I'm not going to test you on any of this. It provides key information about the properties of an element. You get really familiar with that in lab. It shows how electrons are organized. You get familiar with that in lab. And it provides important details about how atoms will react with each other. And you'll get familiar with that in lab. So once again, if you're a note taker, you can just write down that you don't need to study this. There's nothing to study here. I'm just saying, hey, here's why we're going to use a periodic table. Just so you know, this is why. And here's the periodic table. There's all kinds of different versions of them. I don't remember if this is from your textbook or the old textbook, but anyway, there it is. And they kind of singled out hydrogen right here. You can see that some of them are solid, some of them are liquid, some of them are gas. You don't need to know any of that. Yeah. And again, you will use it a little bit, but not much. Generally speaking, it might be like, here's how you have to use the periodic table. I'll say, oxygen's symbol is O. And then I'll ask you some questions like, how many protons does it have? So then you look it up, and you're like, oh, there's oxygen. Its atomic number is 8, therefore it has 8 protons, right? It'll be that kind of question. Or then it might even get even trickier, and I'll say, oxygen's atomic number is 8, and let's just say it has a neutral charge. How many electrons does it have? So that's a step further. Then you look it up again. Okay, oxygen has 8, so that means it has 8 protons, and if it has no charge, it must also have 8 electrons. Right? It would be nice and simple like that. So any questions about the periodic table? All right, so let's go back to this concept of atomic mass and the idea that not every atom of the same element has the same atomic mass, right? Because some of them have different numbers of neutrons. We know they don't have different numbers of protons because, again, to reiterate, you need to know this. If you change the number of protons, you change the element. If you give this oxygen another proton, it becomes fluorine. If you take away a proton from this oxygen, it becomes nitrogen, right? You cannot change the number of protons without changing the element. But again, like we were talking about earlier, using that hydrogen as an example, one of them had no neutrons, one of them had 2 neutrons, one of them had 1 neutron, right? So you can change the number of neutrons, and this is something you need to know for the exam. That is called an isotope. So when you talk about an isotope is something, 2 different things, or at least 2. They're the same element. These atoms are the same element, but they have different number of neutrons. That's the most important thing you need to know. Also, coincidentally, and it's not important for you for the exam or for any problem solving, but this kind of describes why it's important for biology. Even though they have different number of neutrons, they behave identically. And that would be important for a conversation we're going to have later, but I'm not going to test you on that. The most important bullet point for you is isotopes have the same number of protons and the different number and electrons, the different numbers of neutrons. Another way of saying that is, if you change the number of neutrons, you get an isotope. Sort of like earlier I said, if you change the number of protons, you get a new element. Well, if you change the number of neutrons, you get an isotope. I'll put a big X through here. Carbon is the example that I'm using to show you different isotopes of carbon, but you don't need to memorize anything about this. But yeah, so, we've got carbon-12, has a mass, they all have a mass, they all have 6 protons, right? So 6 plus what equals 12? 6 plus 6, right? Carbon-13, obviously it must have 6 protons, otherwise it wouldn't be carbon. So 6 plus what equals 13? 7. Carbon-14, obviously it has 6 protons, because if it doesn't, it wouldn't be carbon. 6 plus what equals 14? 8. So again, like I said before we started talking about isotopes and mass number and averages and all that, if for some reason this doesn't click with you, you're not getting it, don't worry about it. It'll help you a little bit later in the semester, but not a lot. So even if you completely don't understand this, you can still pretty much understand the things I will teach you later. And there won't be a lot of questions about it, so it's not going to devastate your grade. Of course, if you don't understand, the better thing to do would be telling you. Maybe we could meet during office hours or outside of office hours and I can explain it. But anyway, any questions about isotopes? So here's something to think about. So far, I've told you what happens if you change the number of protons. Now I'm telling you what happens when you change the number of neutrons. As you might guess, soon I'm going to tell you what happens when you change the number of electrons. We're getting there. The next word for attendance, compliment. You pay someone a compliment. And if you are online, yes, that is just one word you can send. You don't need a picture. You don't need to tell me your favorite compliment. Just send the word compliment. Because today is also National Compliment Day. On top of that, the other things I said. Anyway, let's move forward if there's no questions about isotopes. No, well, here again, isotopes, right? Same thing that was on the previous slide, but now you're seeing it again. And once again, right, carbon's mass number, right, 12.011. There is no carbon in the universe that has that mass. That's just the average of all the carbons in the universe that we know of. If you want to write a complicated independent work paper, look that up. How the hell do we know the average of all the carbons in the universe? We haven't even been to the whole universe. Who's figured that stuff out? And how did they figure it out? Prepare yourself for a deep dive if you write that paper, because obviously it's not going to be an easy answer. But you could look that up for independent work if you want. And again, there is no minimum or maximum. So if you start writing your paper, like, oh, this is how it goes, and then you get bored with it, like, okay, that's enough. And then just sum up, finish what you're writing, and turn it in. Anyway, that's just an example. I'm not going to test you on that. Again, like I was talking about, I'm pretty sure that's a fake picture, but nonetheless, people do have extra digits, and that's like I was saying, like, what's the average number of fingers, or in that case, toes that humans have? That's just a gross exaggeration of what I was saying. Here's something that's not in your textbook, so I'm not even going to talk about it. Really, I just wanted to mention this one thing. If you ever heard of carbon dating, this is how that works. So you can read about it if you're interested, but I'm not going to ask about it. Basically, radioactive isotopes, they are isotopes, except that they're radioactive. And what does that mean? That means they're giving off parts, right? They're losing some neutrons here and there. And they do it at a rate that scientists know. So they can tell, and you can read this if you want, it's a little bit complicated, but they can tell by looking at the ratio of how many carbon 12s versus carbon 13s versus carbon 14s, how long ago that thing must have died. So again, read this if you want. I find it interesting, but I'm not going to ask you anything about it. It's not in your textbook. Another good independent work topic if you want. It's all about carbon dating. So are these other slides. All right, now we're getting to some really important information. And you're going to get really familiar, very familiar with this in lab. So this is great timing. I'm introducing you to this now, and then next week, we're going to really learn about it in lab. So as far as we're concerned, when we talk about chemical reactions, this isn't 100% true, but for this 100 level non-biology major course, this will suffice for us. As far as we're concerned, it's only the electrons that are directly involved in chemical reactions. As far as we're concerned, it's all about the electrons. So when we're thinking about chemical reactions and molecules and chemical bondings, for us, in this course, you should only concern yourself with electrons. Nothing else really matters. There are a lot of exceptions, but in this course, there will also be a few exceptions, and we'll cross that bridge when we get there. Another way of saying this first bullet point is it's the number of electrons that determines its chemical properties. This is a very important part. This will really help you in lab next week. You definitely need to know this stuff. Again, like I said, a lot of times you'll see an atom drawn this way. Like, I don't know, there's the nucleus inside, and then you've got the rings of electrons on the outside. And again, I just want to reiterate one more time, in reality, it's not actually like that. But this is a great way to teach it so you can learn what you do need to know. So that in mind, again, there's just rings, right? Rings almost like the solar system with the sun in the middle and planets orbiting, right? So, sort of. Anyway, these have rings on the outside where the electrons are. And you definitely need to know this. The first ring only holds 2 electrons. And it's not necessarily that will be a question where I say, how many electrons does the first ring hold? You need to know that to do some problem solving that I'm going to give you later. So to answer these questions that I'm going to give you later, you're going to need to know, all right, the first ring holds 2 electrons. As far as we are concerned, every other ring past that holds 8 electrons, which really comes down to 4 pairs. And as far as I'm concerned, the whole 4 pairs part doesn't matter. We don't discuss it. Technically, when you draw them correctly, like for example, like I said, here we go. 2 electrons on that inner ring, and then 8 on the outer ring, right? So 1, 2. If you were to draw it correctly, not that it matters, I'll never take points away from this. You should draw them in pairs, right? So there we go. There's our 4 pairs of electrons. But as far as we're concerned, it doesn't matter that they're pairs. But what you definitely need to know is the first ring holds 2. As far as we're concerned in this class, everything else holds 8. If you're really familiar with that concept and not afraid of confusing yourself for independent work, you can look that up. Because I'm telling you, it's not actually every single ring after that holds 8. It does change. You can look it up for independent work if you want. But as far as learning what you need to learn in this course, as far as you're concerned, every ring after the inner ring holds 8. Here's another very important part, is this last little bullet point. Because we're talking about chemical reactions here, right? We're talking about the chemical properties. If the outermost ring, whether it be the first one or the second one or the third one, whichever, if the outermost ring it's full, that means it's a stable atom, which means it's not reactive. It's not going to do chemical reactions. It doesn't need to. It has a full outer ring, and it is happy. Now, don't get me, keep in mind too that sometimes the outer ring is only the first ring. So hydrogen has only that one ring, right? It's got the one proton, has the one ring, has the one electron. That is not a happy atom because the inner ring holds two. It only has one. It's going to be reactive. It wants another electron. Helium, on the other hand, with its two protons, also has two electrons. Helium is not reactive. It's chill. It's got a full outer ring. In this case, the outer ring also happens to be, the outermost ring also happens to be the inner ring, because it only has one ring. But its outermost ring is full, so it's happy. It does not need to give up any electrons. It doesn't need to take any electrons. It doesn't need to share electrons. It's happy. So keep that in mind. Whenever something has a full ring, it is not reactive. And there will be a test, I think this is a pre-lab question, where I give you enough information where I'll tell you like how many electrons something has maybe, and then you can just draw it. You just draw the rings, and just draw all the electrons, and if it doesn't have full rings, it's reactive. If it does have full rings, wait, did I say that right? If it does have full rings, it's not reactive. If it does not have full rings, it is reactive. Any questions so far? Okay, so all that being said, this is what chemical reactions are as far as we're concerned. Chemical reactions are just atoms trying to be happy. They're just trying to get those full amount of electrons. And that reactions enable atoms to transfer or share electrons. And this is what keeps them close together. That's what chemical bonding is. This is where we get molecules. So if it wasn't for this, we wouldn't have anything. We wouldn't have life as we know it. We would only have all the elements on the very right-hand side of the periodic table. We would have no molecules, therefore nothing alive. Nothing big. Everything would be just so tiny. So once again, it's the chemical bonds, or in chemical bonds, it's the atoms that are trying to fill their outer ring. Hence the octet rule. And let me put this out there too. I'll put an X through octet rule. I only included that because it's in your textbook. So basically, I've explained to you what the octet rule is. All that stuff I just explained, meaning that the outermost ring, if it's not the first ring, holds 8 electrons. That's what that means. Now, I only introduced you to that term because it's in your textbook. I don't plan on using that term again for the rest of the semester. Any questions about this slide? All right, so again, we're talking about chemical bonds here, right? So almost all the elements do need electrons or do need to give up electrons. Almost all electrons don't have that full outermost ring. So they do want to do chemical bonds. So let's talk about chemical bonds. This might be our last slide for the for the day. This slide is not from your textbook, so if you're trying to study it, you're going to need to look at the PowerPoint, not the textbook. But cells are constantly rearranging molecules and breaking bonds and forming new ones. As a matter of fact, that's what keeps us alive. When you break bonds, you're releasing energy, and we'll talk a lot about that later. So if it wasn't for the breaking of bonds, we wouldn't be releasing energy, and we wouldn't have life. We wouldn't be here. So that first bullet point, definitely not a test question. This is more like, hey, why do we even have to learn this? Why is this important for biology? Well, that's why it's important for biology. Because this is happening a lot. Cells are doing this. In your old textbook, and you don't need to know this either. Actually, I'll put it next to that. Again, you don't have to know that. You don't need to know this either. But the old textbook defined chemical reactions as changes in chemical composition of matter. What you do need to know are these two things right here. The reactants are the starting material, and the products are the end material. Which hopefully should be easy to memorize because it's kind of in the name. When we're talking about chemical reactions, the reactants are the things doing it, right? Products, that's really easy, right? That's the product of the chemical reaction. Another thing that'll help you in this course anyway, in this course, reactants are always on the left-hand side of the chemical reaction. Products are always on the right. In this course. It's not always like that in real chemistry. And in this course, there will always be an arrow pointing from the reactants to the products. For your own knowledge, just so you know, a lot of times chemical reactions go both ways. Like the reactants will turn into the products, and if you do things the right way, you can also turn the products back into the reactants. As far as we're concerned, we're keeping things simple. Reactants on the left-hand side, products on the right. The arrow always points from the reactants to the products. You need to know that. And then not this is going to be a test question, but these 2 bullet points is good for your understanding. We only rearrange matter in chemical reactions. We cannot create or destroy matter. That is a law of nature. We cannot create or destroy matter. We can only rearrange it. And this is a great example. How many of you ever had like a little cut or something, you put hydrogen peroxide on? What happened when you did that?
Bubbles up.
Bubbles up, right? And this shows you why. We put these, here's 2 molecules of hydrogen peroxide on the left. And notice we have 2 oxygens, 2 hydrogens. 2 oxygens, 2 hydrogens, right? So in total, we have 4 oxygens and 4 hydrogens, right? You put it on your wound, like he said, it starts bubbling up. What are bubbles? Liquid and gas, right? So here we go. We have 2 molecules of water and 1 molecule of oxygen, hence the bubble, right? Liquid and gas. But also, look, we've rearranged things. We no longer have 2 hydrogen peroxide molecules. We don't have any hydrogen peroxide molecules anymore. Now we have water and oxygen. But look, 1, 2, 3, 4 oxygens, 1, 2, 3, 4 oxygens. 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 hydrogens. So again, we didn't create or destroy anything. We just rearranged it. The last word for attendance is Diamond, Neil Diamond's birthday. And again, don't forget, especially for those of you online, you also need to come up with 1 question about all this stuff that I presented. Even if you think you understand everything, I don't know, pretend like you're writing a test question and send in 1 question. Make sure you get it in before 9 a.m. And that's it. I'll see you guys next week unless you need me for office hours.
Can you just send the question to the doctor or something?
Oh, great question. So for the attendance words or questions like that, you can just email them to me.
Email.
For independent work, you will share it with via Google Docs. Oh, I forgot one reminder. It's not that important, but just so you guys know, like as you see, like when you turn in a pre-lab and labs, I can do a lot of online feedback. I just want to make sure you understand my tone. A lot of times, if you ask me a question that I already answered, I'll remind you of that, not to be like, I already told you, idiot. I'm not doing that. It's more like I'm trying to jog your memory. So like I'll answer the question. I'll say something like, as I said in lab, blah, 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 blah. It's not like I'm being a jerk and making you feel bad for forgetting. I'm just trying to jog your memory.
Can I send a question I already know the answer to?
Sure. Well, I guess and no. Yes, you can, but you still need a source. So even if you know it, you still have to have a source to prove that you're right. That make sense? That's good practice.
I'm saying for the
Oh, yes.
for the words, for the
Yes.
Latin words.
Yeah. Like I said, you can know it, and that could, yeah.
Wait, was there a question you had to answer?
No, for the extra credit, for all the words, if you were to send me a question of something, like you didn't understand something or you want to verify, if you send it to me, you just get even more extra credit for being there. That's all.